I think maybe we can start with other 2 minutes. Okay, so we can start. It's a pleasure for me to introduce Dr. Lucia Armillotta, who got her PhD here in 2016, so maybe many of you know her since then. And so she had a thesis on the multi-phase circumgalactic medium in this galaxy using hydrodynamical simulation, so she is a theoretical astrophysicist. Then she moved to Canberra, Australia, for a postdoctoral fellowship, and she stayed there until 2019. And since then, she is an associate researcher at the Princeton University. And so now she works on the cosmic ray transport and feedback, so the floor is yours.
Thank you. Good morning, everybody. I am very excited to be back in this department after more than 7 years since my PhD. So it's a real pleasure. Today I will talk about cosmic ray transport and feedback in star-forming galactic disks. First of all, what are cosmic rays and why are they important? Cosmic rays are high-energy non-thermal particles that are mainly produced within galactic disks through shock acceleration in supernova remnants. On the right, you can see the cosmic ray energy spectrum measured from the Earth. In particular, on the x-axis, we have the kinetic energy in GeV per particle, while on the y-axis, we have the cosmic ray flux multiplied by the square of the energy. And you can see that the spectrum extends over more than 10 orders in kinetic energy. The flux is dominated by protons and heavier nuclei, followed by electrons. For the protons, the spectrum is basically a broken power law that peaks at kinetic energies of a few GeV. Now, from the spectrum, we can integrate the spectrum to compute the cosmic ray, the total cosmic ray number density and energy density. The cosmic ray number density is very low, is about 10 to the minus 10 particle per centimeter cubed. And this means that it's almost 10 orders of magnitude lower than the average gas density in the ISM. However, despite this very low number density, the cosmic ray energy density, that is about 1 electron volt per centimeter cubed, it's in equipartition with the thermal, kinetic, and magnetic energy densities in the ISM. So this suggests that cosmic rays can have a fundamental impact on the dynamical state of the interstellar medium, and in doing so on the evolution of galaxies. Let me say that cosmic rays influence the dynamics of the background gas by exerting pressure gradient forces on the gas. As I said, cosmic rays are mostly produced within the galactic disk, so therefore their energy decreases moving away from the galactic disk, and the resulting cosmic ray pressure gradient force can potentially counteract the gravitational potential of the galaxy, driving flows of material away from the disk. Now, from a theoretical point of view, studying the effect of cosmic rays in galaxies is not trivial, because this requires connecting the kiloparsec scales of galaxies to the microscopic scales of the cosmic ray gyro radius. In my work, I'm mostly interested in GeV cosmic rays with kinetic energies of a few GeV because they dominate the energy spectrum and are therefore dynamically important for the surrounding gas. And for GeV cosmic rays, the gyro radius is less than 1 AU. So it's comparable to the Sun-Earth distance. So you can understand that with a scale separation of 10 to the 10, it's impossible to track individual cosmic ray gyro orbits in galaxy scale simulations. So if we want to model the effect of cosmic rays in galaxy simulations, we need to develop a fluid theory for this collisionless non-thermal plasma. So what is the microphysics that we need to model? Well, as I said, the number density of cosmic rays is very, very low. So this means that collisional interactions between cosmic rays and thermal gas are not very frequent. So cosmic rays interact with the gas mostly via collisionless interactions that are mediated by the magnetic field. In the presence of a uniform magnetic field, being cosmic rays charged particles, they gyrate around and stream along magnetic field lines. Now, when they encounter alpha waves that are transverse fluctuation of the magnetic field, so when they encounter alpha waves with a wavelength comparable to the cosmic ray gyro radius, the pitch angle scatter of these waves. The pitch angle is the angle between the cosmic ray velocity direction and the mean magnetic field direction. And this angle changes as cosmic rays interact with the alpha waves. And the rate of cosmic ray scattering is proportional to the fractional magnetic field variation. Now, for GeV cosmic rays that are the main focus of my work, these alpha waves are mostly driven by streaming instabilities. If the cosmic ray drift speed is larger than the local alpha speed, the seed alpha waves are unstable and get amplified by the cosmic ray themselves through gyro resonance. Now, as you can see from this equation, if the wave amplitude increases, the cosmic ray scattering rate increases, and this process traps cosmic rays within the alpha wave frame of reference, or in other words, this process forces cosmic rays to reduce their propagation speed and stream at the same velocity of the alpha waves. However, it is also true that there are several damping mechanisms that can cause these waves to dissipate. So in case of weak wave damping, there is a strong coupling between cosmic rays and alpha waves, and cosmic rays propagate together with the alpha waves, while in case of strong damping, the rate of scattering is relatively low, and cosmic rays mostly diffuse relative to the alpha wave. Now, this entire process of cosmic ray scattering allows cosmic rays to interact with the thermal gas. As cosmic rays couple to the scattering alpha waves, the magnetic field mediates transfer of momentum and energy from the cosmic ray population to the thermal gas. Now, how do we go from the microscopic scales where cosmic ray scattering takes place to the macroscopic scales of galaxies? Or in other words, how do we describe the transport of cosmic rays as a fluid? Now, generally, the propagation of the cosmic ray fluid is treated as a combination of these three mechanisms: advection, streaming, and diffusion. So let me say a few words about each of these processes. First of all, cosmic rays are advected by the background gas because, as you know, magnetic fields are flux frozen in the gas. So if the gas moves, magnetic fields and cosmic rays move together with the gas. And then relative to the gas, the propagation of cosmic rays is a combination of streaming and diffusion along the magnetic field lines. Cosmic rays stream at the local ion alpha speed in the direction of decreasing pressure, and depending on the degree of coupling between cosmic rays and waves, they can propagate faster than the alpha waves, or in other words, they diffuse relative to the alpha waves due to pitching or scattering. Now, in galaxy scale simulations, this process of cosmic ray wave interaction cannot be resolved. So cosmic ray diffusion is generally parameterized by this coefficient sigma. It is called scattering coefficient, but is generally assumed to be constant. Now, given their potential dynamical impact on the ISM, studying studying the effect of cosmic rays in galaxies has been central in recent galaxy evolution studies. Recent MHD simulations, including a cosmic ray fluid, have shown that cosmic rays can play an important role in regulating the level of star formation in galactic disks or in driving large-scale galactic outflows. However, the extent to which cosmic rays affect these phenomena is very sensitive to the treatment of cosmic ray transport in the model. Now, to give you an idea, these two plots show the gas density distribution in the top left and cosmic ray energy density distribution in bottom right of Milky Way-like galaxy as predicted by 6 different simulations with different prescriptions for cosmic ray transport. So in each plot, the first 3 panels show the predictions of simulations without magnetic fields. This means that there is no preferential direction for cosmic rays. The bottom 3 panels show the predictions of simulations with magnetic field. However, the simulation in the left panel does not include cosmic ray diffusion. The simulation in the central panel does not include cosmic ray streaming. The simulation in the third panel include all the possible transport processes. Well, from a visual comparison between these 6 panels, you can see that the final distribution of gas density and cosmic ray energy density is strongly sensitive to the underlying cosmic ray transport assumptions. Another limitation of most MHD simulations of galaxies is that the cosmic ray scattering rate is assumed to be constant, based on empirical estimates in the Milky Way. However, given the variety of conditions present in the multi-phase interstellar medium, a constant scattering rate is highly unrealistic. So with my work, we tried to rectify this situation by characterizing the transport of cosmic rays in ISM simulations with in a more physical and realistic way. We started from the 2-moment algorithm for the transport of the cosmic ray fluid implemented in the MHD code Athena++. This algorithm was designed to follow the transport of one single cosmic ray fluid, assuming that all cosmic rays are characterized by a single kinetic energy of 1 GeV, because GeV cosmic rays are those important for the gas dynamics. So one single cosmic ray fluid, and the scheme is composed of 2 equations. The first equation describes the evolution of the cosmic ray energy density. The second equation describes the evolution of the cosmic ray energy flux. So let me briefly focus on the first equation. Here, EC, FC, and PC are the cosmic ray energy density, cosmic ray energy flux, and cosmic ray pressure tensor. Now, the left-hand side of this equation describes the transport of cosmic ray energy density in the simulation frame. And in the absence of terms on the right-hand side, it would represent cosmic ray energy conservation. The terms on the right-hand side are source and sink terms. For example, the first term describes the work done on or by thermal gas. The second term describes the rate of transfer of energy from the cosmic ray population to the gas via wave damping. The third term describes the rate of energy losses due to collisional interactions of cosmic rays with the gas. And for GeV cosmic rays, the dominant collisional processes are ionization and pion production, while the fourth term describes injection of cosmic rays due to supernova explosions. And we assume that 10% of supernova energy goes into production of cosmic rays. The second equation is the equation for the evolution of the cosmic ray energy flux. And here the right-hand side encodes the information about the interaction between cosmic rays and waves that is unresolved on macroscopic scales. In particular, sigma tot encodes this information. Sigma is a tensor that in the magnetic field frame of reference can be written in this way. This means that in the direction parallel to the magnetic field, sigma tot allows for streaming at the ion alpha waves and diffusion relative to the waves. Here, sigma parallel is the scattering coefficient that I mentioned in the previous slides. Finally, we need a closure equation to close this set of equations. And in most astrophysical applications, we can assume that cosmic rays are closed to be isotropic, so the cosmic ray pressure is 1/3 of the cosmic ray energy density. Now, as I said, with my work, we try to go beyond the classical assumption of constant cosmic ray scattering. So we move beyond this assumption, and we derive an expression for the cosmic ray scattering coefficient that depends on the gas properties, on the properties of the gas and cosmic ray themselves. Now we compute the scattering coefficient sigma, assuming that the scattering the growth of the alpha waves is balanced by damping processes that cause these waves to dissipate. So we set the alpha wave growth rate equal to the damping rate, and we compute sigma from these equivalents. In particular, we consider two different damping processes, namely ion-neutral damping and nonlinear Landau damping. Ion-neutral damping occurs in partially ionized gas, where waves propagate in the ions and in the magnetic field only and are damped by collisions of ions with neutrals, while nonlinear Landau damping happens when thermal ions have a Landau resonance with the beat wave formed by the interaction of two resonant alpha waves. Anyway, so we compute sigma under the separate assumption that the alpha wave growth rate is equal to the ion neutral damping rate, and that the alpha wave growth rate is equal to the nonlinear Landau damping rate, and we set the final value of the scattering coefficient equal to the minimum between these two values. Now, we used this code that I just described to compute the transport of cosmic rays within the Tigris MHD simulations of portions of galactic disks. The advantage of these local disk simulations is that star formation and supernova feedback are modeled in a self-consistent way, thus providing a realistic representation of the multi-phase interstellar medium. Now, the original Tigris simulations do not include cosmic rays, so the transport of cosmic rays is computed in post-processing. What I mean is we select a number of snapshots from this simulation, and given the frozen distribution of thermal gas, magnetic field, and star particles, we let cosmic rays evolve until a steady state is reached. Now, in this movie, you can see, so this is a movie of the Tigris simulation modeling the solar neighborhood environment. From left to right, we have star particle position and ages, gas density projection, gas number density, gas temperature, gas pressure, gas velocity, and magnetic field strength. And you can see the galactic disk is located here at around z equals 0, and it is characterized by a thickness of a few hundred parsec. Also, you can see that stellar activity within the disk drives multi-phase outflows out of the plane. These outflows are composed of hot and fast-moving gas embedding warm, cold, slow-moving filaments and clouds. Now, we computed the transport of cosmic rays within 3 different galactic environments simulated with Tigris. The properties of the 3 environments are listed here. They are called R2, R4, and R8. And together, these 3 environments cover a wide range of galactic conditions in terms of star formation rate, surface density, gas surface density, and gravitational weight. So among these 3 models, R8 is the model representative of the solar neighborhood environment. And for example, you can see that the star formation rate surface density varies by more than 2 orders of magnitude, going from R2 to R8, as well as the mid-plane pressure. Now, before talking about the predictions of my model with a variable scattering coefficient, I would like to show you the predictions of the model with a constant value of the scattering coefficient. Here, the first set of panels shows the distribution of cosmic ray pressure predicted by 3 different models with 3 different values of constant sigma. 10 to the minus 27, 10 to the minus 28, and 10 to the minus 29 seconds per centimeter squared. And you can see that the distribution of cosmic ray pressure becomes smoother as we move from left to right. So as the scattering coefficient decreases, because diffusion becomes more and more important. The second set of panels show the distribution on grid of gas density, gas temperature, and gas velocity. And from a visual comparison, you can see that except for this model with high diffusivity, the distribution of cosmic ray pressure in the other 2 models is nearly follows the gas distribution. Cosmic rays accumulate in the galactic disk, where in the galactic disk and in a few warm clouds at higher latitudes, where the relatively low gas velocity do not facilitate their propagation, while cosmic rays in hot and fast-moving winds are quickly advected away from the plane. And this can be understood looking at this second plot. Here, the 3 colored lines indicate the mean vertical profiles of cosmic ray pressure as predicted by the 3 different models. You can see that the profile predicted by the model with a low value of sigma, color-coded in green, is relatively flat, while the profile predicted by the model with a high value of the scattering coefficient peaks near the galactic plane and then decreases at higher latitudes. Now, the take-home message of this slide is that the cosmic ray pressure distribution is very sensitive to the choice of the scattering coefficient, and so one should be very careful before choosing this constant value, because different cosmic ray pressure distributions can then lead to different effects of cosmic rays on the gas. Now let's move to the predictions of models with variable scattering coefficients. Here from left to right, we have slices of gas density, gas temperature, gas velocity, ion alpha speed, cosmic ray scattering coefficient, cosmic ray pressure, and cosmic ray flux. And let's focus on the distribution of the cosmic ray scattering coefficient. So you can see that sigma is relatively high and constant in the hot, warm, low-density gas of the extra-planar region, while it is much lower than 10 to the minus 29 in the high-dense, in the dense, mostly neutral gas of the galactic disk. Now, just let's look at this plot showing the average value of sigma as a function of gas density. So the solid line shows the average value of sigma, while the dashed and dotted lines show the value that sigma would have if the only damping mechanism at play was nonlinear Landau and ion neutral damping. Now, in the low density regime, sigma is almost independent of the gas density. In this regime, nonlinear Landau damping dominates. In the high density regime, however, sigma quickly decreases with increasing gas density. So there is a almost 4 order of magnitude variation. In this regime, gas is mostly neutrals, so waves are efficiently damped by collisions of ions with neutrals. Now, moving to the cosmic ray, to the vertical cosmic ray pressure profile predicted by this model with a variable scattering coefficient, in comparison to the pressure profiles predicted by model with a constant value of the scattering coefficient. So you can see color-coded in red. So this is the mean cosmic ray, the vertical profile of cosmic ray pressure predicted by the model with a variable scattering coefficient. And you can see that this profile is very similar to the profile predicted by the model with a high value of the scattering coefficient. While near the midplane, the cosmic ray pressure is comparable to that predicted by the model with an intermediate value of the scattering coefficient, and it is much higher than the cosmic ray pressure predicted by the model with a low value of the scattering coefficient. And this is surprising because we have seen that in the galactic disk, the scattering coefficient is actually very, very low, much lower than 10 to the minus 29. So this means that even though cosmic ray diffusion is highly effective in the galactic disk, the propagation of cosmic rays out of the disk depends on the propagation properties in the warm gas surrounding the disk, where the scattering coefficient is much higher. Now, briefly, I would like to comment, so let me skip this. So I would like to comment on the relative importance of different cosmic ray transport mechanisms that are advection by the background gas, streaming together with the alpha waves, and diffusion relative to the alpha waves. Now, in the plot on the right, you can see the mean values of the 3 components of the cosmic ray propagation speed as a function of gas density. And you can see that in the low density regime, advection largely dominates. In the high density regime, diffusion dominates, while at intermediate densities, streaming becomes more important. Now, the take-home message of this plot is that cosmic ray transport can be quite different in different thermal phases of the gas. Therefore, it's very important to resolve the ISM structures in cosmic ray studies. Now, among the 3 environments modeling the solar, the 3 environments post-processed with our code, let's first focus on the solar neighborhood environment. In the plot on the right, the purple line shows the average vertical profile of cosmic ray pressure, while the other lines indicate the mean vertical profiles of thermal, magnetic, and turbulent pressures. Now, it's interesting to note that our model with a self-calculation of the scattering coefficient predicts a cosmic ray pressure near the midplane in equipartition with the other pressures. And this is in agreement with the observations in the local ISM. Also, the value of the cosmic ray pressure near the midplane is in agreement with observations from the Earth. Now, speaking about comparisons with observations, I would like to open a parenthesis and show you a preliminary work that we are doing towards a more accurate comparison with observations of cosmic rays in galaxies. So we are, as I told you at the beginning of this talk, a limitation of the scheme that we are using is that it follows the propagation of one single cosmic ray fluid, assuming that all cosmic rays have a kinetic energy of 1 GeV. Now, while this is justified by a dynamical point of view, this treatment does not allow for investigation of higher energy cosmic rays whose non-thermal emission is a very powerful observable. So we are now moving beyond the single fluid treatment, and we have recently extended the code in order to track the propagation of multiple cosmic ray fluids, each of them representative of cosmic rays within a given range of kinetic energies. So far we have used this code to post-process the Tigris simulation modeling the solar neighborhood environment. And in these post-processing simulations, we consider we followed the transport of both cosmic ray protons and cosmic ray electrons, and we investigate the spectral range between 1 GeV and 100 GeV. Now, depending on the typical kinetic energy, different cosmic ray fluids undergo different energy losses and different scattering rates. As you can see from this plot, from our self-consistent calculation of the scattering coefficient, we find that the scattering coefficient decreases with increasing cosmic ray kinetic energy, meaning that cosmic ray diffusion is more important at high kinetic energies. Now, just let's move to the predictions of these simulations. Here we have from left to right slices of gas density, gas pressure, gas density, gas temperature, and cosmic ray and energy density for cosmic rays with kinetic energy of 1 GeV, 12 GeV, and 100 GeV. In this other plot, I'm showing the cosmic ray spectra. The dashed lines indicate the injection spectra for both protons and electrons, while the solid lines indicate the average spectra measured in the ISM. Now, the slope of the injected spectra is minus 2.3 based on observations. So this is fixed, and this value is based on both observations and simulations of cosmic ray acceleration in shocks. Then the spectra of cosmic rays become steeper as they propagate through the ISM, and the average spectral slope is in the ISM is minus 2.7 for the protons and minus 3 for the electrons, and this is in very good agreement with observations in the local ISM. Now we are also what we are doing right now is we are combining the cosmic ray electron spectra predicted by our post-processing simulations with the magnetic field distribution given by the original Tigris simulations in order to infer the distribution of synchrotron emission in a solar neighborhood-like environment. As an example, here I'm showing the rightmost panels show the distribution of magnetic field strength and synchrotron emissivity at 6 gigahertz. Now, I don't want to go further on this particular project because this is beyond the topic of my talk. But if any of you is interested in synchrotron, in observations of synchrotron emission in our galaxy or nearby galaxies, please come talk to me after the talk. Now, going back to the transport of GeV cosmic rays, as I said, we take a post-processing approach to study the transport of cosmic rays. So, however, we can still use the predictions of these simulations to make predictions about the dynamical impact of cosmic rays on the ISM. Now, as I told you, cosmic rays influence the ISM dynamics by exerting pressure gradient forces on it. And from this plot, so if we focus on the disk region only, you can see that the cosmic ray pressure profile is relatively flat. So this means that the cosmic ray pressure gradients are subdominant compared to other pressure gradients. And so we expect that the contribution of cosmic rays in supporting galactic disks against gravity is subdominant. However, if we move at higher latitudes, the cosmic ray pressure gradients are higher than the other pressure gradients, and this suggests that cosmic rays can efficiently drive flows. I mean, they can have an important effect in accelerating galactic fountains. And now, moving to the other environments investigated the other two environments investigated in our work, we find that the cosmic ray pressure as well as the MHD pressure is proportional to the star formation rate surface density. However, the ratio between the mid-plane cosmic ray pressure and mid-plane MHD pressure is inversely proportional to the star formation rate surface density. Now, the reason is that cosmic ray propagation out of disks is more effective in environments with higher star formation rate. And among the three mechanisms responsible for cosmic ray transport, advection is the one responsible for such behavior. I mean, environments with higher star formation rate are characterized by higher velocity outflows that quickly advect cosmic rays away from disks. So from this result, we expect that the impact of cosmic rays in driving galactic outflows might be more important in relatively quiescent environments like our own solar neighbors. Now, clearly, we need, these are post-processing simulations, and we need fully self-consistent simulations with time-dependent MHD and cosmic rays in order to validate these possibilities. Now, this is the conclusion of the first part of the talk, where we have seen that we have investigated cosmic ray transport in galactic environments typical of Milky Way-like galaxy. And we have seen that it is very, I mean, that a realistic distribution of the background ISM is crucial for a detailed modeling of cosmic ray transport. Also, there is no single diffusivity. Depending on the background gas properties, the scattering coefficient of cosmic rays can vary over more than 4 orders of magnitude. And finally, cosmic ray propagation seems to be more effective in environments with higher star formation rate, where higher velocity outflows quickly remove cosmic rays away from the disk. Now, in the second part of the talk, I would like to focus on the impact of cosmic rays on the dynamical state of the ISM. Waiting for the next generation of Tigris simulations with cosmic rays, we have started to investigate the role of cosmic rays, the contribution of cosmic rays to accelerate galactic winds by means of more simplified simulations. In these simulations, MHD and cosmic rays are evolved together. Now, the initial conditions of these simulations are extracted from the Tigris simulation modeling the solar neighborhood environment. In particular, we focus on the extra-planar region. What I mean is we extract the distribution of the MHD variables from this region above 500 parsec. And this is the domain of our new simulations. During the simulation, we continuously inject thermal gas and cosmic rays from the bottom of the simulation box. And in doing so, we simulate the presence of a continuous outflow coming from the disk. In particular, we explore two different types of outflow, either hot and fast-moving or warm and slow-moving. Both of them are expected to be produced by supernova explosions into the extra-planar region. So let me start from talking about the role of cosmic rays in hot and fast-moving winds. Now, in this simulation, we inject, as I said, gas from the bottom of the simulation box, and this gas as a temperature is very high temperature, about 10 to the 7 K, and high velocity, about 300-400 kilometers per second. You can see that the cosmic ray pressure is initialized with a smooth profile, decreasing towards higher Z. Now, however, as soon as we start the simulation, the initial cosmic ray pressure gradient is quickly disappear. And you can understand that in the absence of a cosmic ray pressure gradient pointing downward, cosmic rays cannot accelerate the gas. And this is confirmed by this plot showing the outward mass flux measured at Z equal 3 kiloparsec as a function of time, both in the presence and in the absence of cosmic rays. Now, in the first part of the simulation, the two profiles are similar. However, in the second part, the outward mass flux predicted by the simulation without cosmic rays is higher than the outward mass flux predicted by the simulation with cosmic rays. This means that somehow cosmic rays are reducing the flux of outflowing gas. So in order to understand such behavior, let's think of the main process driving cosmic ray transport here. So here, most of the gas is hot and fast moving, and as we saw in one of the previous slides, in this regime, cosmic rays are mostly advected by the high velocity ambient gas. So let's then look at the mean vertical profiles of the gas velocity. Here, the red line shows the mean vertical profile of the hot gas velocity, while the cyan line shows the mean vertical profile of the warm gas velocity. So you can see that the warm component, the velocity of the warm component of the outflow increases with Z, because the warm component gains momentum from the hot component as they move away from the disk. On the other side, the velocity of the hot component of the outflow decreases with Z. Now, in this advection-dominated regime, the pressure of cosmic rays is inversely proportional to the velocity of the hot gas. So as the velocity of the hot gas decreases with Z, the pressure of cosmic rays increases. So cosmic rays build up a weak pressure gradient pointing upward that slows down the gas rather than accelerating the gas. Now, moving to the case where a warm and slow-moving wind is injected from the bottom of the simulation box. So the injected gas has a temperature of 10 to the 4 K and a velocity of about 10 kilometers per second. So it's warm and slow-moving. Now, in the absence of cosmic ray pressure, you might expect that thermal pressure forces would become negligible once the hot gas present in the initial conditions escapes the simulation box. However, in the presence of cosmic rays, a cosmic ray pressure gradient pointing downward is present throughout the entire simulation. And the thermal gas adjusts to the presence of such gradient, with the low density gas flowing out and the high density gas falling in. Now, a quantitative analysis of this simulation confirms that cosmic rays can accelerate the gas in this case. So this plot shows the variation of, in this plot, the purple line shows the variation of gas momentum flux as a function of z, while the orange line shows the variation of cosmic ray momentum flux as a function of z. Now, from the momentum conservation law, we know that these two quantities, that in steady state, these two quantities must compensate. And this is the case in our simulation. In particular, the variation of gas momentum flux is always positive and increases with z, while the variation of cosmic ray momentum flux is always negative and decreases with z. This means that cosmic rays are transferring momentum to the gas as they flow away from the disk. Now, what is the difference with respect to the previous simulation where cosmic rays were not able to accelerate the gas? So again, let's think of the main process driving cosmic ray transport here. This plot shows the average vertical profiles of gas advection speed and streaming speed. And you can see that at least at low latitudes, streaming largely dominates over advection. Now, in this streaming-dominated regime, the effective sound speed is inversely proportional to the gas density, meaning that the effective sound speed increases with z as the gas density decreases. And this condition ensures that the effective sound speed is always at least near the wind base, the effective sound speed is larger than the gas velocity. And this requirement is necessary for the gas to be accelerated. Now, let me skip this slide. So I would like to say that in addition to their dynamical effect, cosmic rays are also very important for their thermal effect. So, for example, let's look at this plot. So in this simulation, so this is a simulation where warm and slow-moving gas is injected. So the temperature of the injected gas is 10 to the 4 K. However, you can see that there are low-density regions with much higher temperature, about 10 to the 6 K. Now, in order to understand what is the dominant heating mechanism here, let's look at this equation showing describing the thermal energy evolution. Here on the terms on the right-hand side describe gains and losses of thermal energy due to interactions with the environment. And in particular, in our simulations, we consider collisional radiative cooling, photoelectric heating, and heating due to cosmic rays. The underlying mechanism here is the one that I explained in one of the first slides. So as scattering alpha waves are damped by several damping processes, there is a transfer of energy from the waves to the thermal gas. Now, if we compare the average heating rates as a function of gas density, we can see that in the high density regime, gas is in thermal equilibrium with radiative cooling balanced by photoelectric heating. In the intermediate density regime, photoelectric heating starts to become subdominant, and radiative cooling is balanced by cosmic ray heating, while in the low density regime, the cooling time scales are very large and cosmic ray heating dominates, producing these high temperature, low density regions that we see in this plot. Now, these are my conclusions. I just would like to highlight the main conclusion of the second part of this talk, that is cosmic rays are very effective in driving warm flows of gas out of the plane. Clearly, the simulation that I showed are quite simplified because they do not include a disk region with a self-consistent production of galactic outflows. However, they are very useful to understand under what conditions cosmic rays can accelerate the gas. So in order to understand the interplay between supernova-driven outflows and between thermally driven outflows and cosmic ray-driven outflows, we are now working on the next generation of Tigris simulations with cosmic rays. So stay tuned for these new results. Thank you.
Before starting with the questions, I would like to remind the students that they will have dedicated time after